Hi guys, today we're going to be looking at a problem involving the free fall motion of an object in one dimension. So the equations of motion here I've written out are going to play a big role, but today I'm going to focus on, in this video, I'm going to focus on the free fall motion aspect. So the first thing we want to do before we move on is define what it means to be in free fall motion. So what that means is fairly simply, if an object is only being accelerated by gravity, we say it is in free fall motion. So the easiest way to really get a handle on what that means in terms of what we want to use it for is going to be to look at the simple scenario where we throw a ball up in the air and it falls back to the ground. So in that instance, as soon as we let go of the ball, we say that the ball is in free fall motion because the only acceleration it's experiencing is gravity. So we can draw out this scenario here. And so we're going to say that this is a ball that we've just thrown up. And so physically that means that we've given it some initial velocity. We'll call that v0. And again, it's always good to pin down your coordinate system. So let's call wherever we let go of it, y is equal to 0. So again, as we know, this is acting in a gravitational field. And so we have some gravity vector pulling the ball back down to the ground. So we've started with some initial velocity v0. So now let's look a couple seconds later. We know the ball will have risen some amount. And if we just think intuitively of what's going to happen, the ball is going to rise and be slowing down all the way to the top. And then it's going to start falling back down to the earth. So that amounts to, we will have a smaller velocity vector a couple seconds later after it's risen a few meters. And so the reason this happens physically is because we have a velocity vector pointing up and a gravitational acceleration vector pulling down. So anytime we have an acceleration vector pointing exactly directly opposite to a velocity vector, it's going to work to make this velocity vector smaller. So that's what it means when we say the ball is slowing down on the way up. And then we see that if we extend that all the way to the top of its motion, that means all the way at the top, it's sort of going to pause at the very top for an instant before it falls back down. And so this is important, and we'll use this fact today, which is that at the top of its motion, its velocity is 0 in the y direction. That's when this velocity vector has gotten smaller, 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 all the way to 0. And so then we can look on the way back down as well. We know here's the top, and we think if it falls down a couple meters, it's now going to have some velocity vector pointing downwards. So that's to say, as it's falling down, the gravitational acceleration vector is pointing in the same direction as this velocity vector. So it's going to work to make it bigger. So as it's reached all the way down to where it started, it's going to have sort of this opposite velocity vector, and it's going to be increasing in size because the gravitational acceleration vector is pointing in the same direction here. Okay, so let's read the problem statement and try to figure out where we want to start. So the problem statement is as follows. Sam heaves a 16-pound shot straight upwards, giving it a constant upward acceleration from rest of 35 meters per second squared for 64 centimeters. He releases it 2.2 meters above the ground, and the problem tells us we can ignore air resistance. So what we're going to be concerned with here is how high above the ground does the shot go? Okay, so if we think about what we've just read, we can see that this problem splits up very naturally into two different stages of motion. So in our first stage, Sam is accelerating the shot upwards, and our second stage, he lets go and it's in free fall motion until we get to the top of the motion. So we also want to think about what they're asking, and so they ask for the height that it reaches. So that really just means what is the position above the ground that the shot reaches at the top of its motion. So let's start by drawing our diagram here. So this will be the ground, and I'm going to draw each stage in a separate color so that we keep in mind these are distinct and we'll have to deal with them separately. So right here I'm going to draw, this is the shot starting from rest, and this is the stage where Sam is accelerating the shot upwards. And so we know that this is going to occur for some amount of a distance, and then at some point he's going to let go of it, and it's going to have some initial velocity from the acceleration. And so then this will be stage, I'll label these stages as well. So this will be stage B, and then let's label this stage here as stage A. So once we have our diagram sort of drawn right here, we're going to want to label our coordinate system. So I'm going to label the ground as our 0 point for our coordinate system. So this is good to keep in mind because the problem asks us for the height above the ground. So anytime we solve now, any height that we solve, so any position we solve for is implicitly defined above the ground. So that's going to be helpful for this problem. And so then the other thing we know is that there's going to be an acceleration vector due to gravity pulling this object downwards. So one last thing for this diagram is I'm going to draw on a couple of the distances they give us. So this is going to help us down the road to sort of just, on this diagram, pin down some distances. And so what they tell us first is they say he lets go of the shot 2.20 meters above the ground. So that's to say when stage 2 starts, the motion of stage 2, so the free fall starts, it's going to be 2.20 meters above the ground. And then similarly, it tells us also that this motion here, when it's being accelerated, occurs for 0.64 meters. And so this is given to us in centimeters, so I've converted directly to meters. So now that we have these distances here pinned down, we can sort of look at our table of knowns and unknowns, and everything will sort of fall into place from this diagram. So I'm going to draw this table here. And so I'm going to first start by looking at the first part of the motion, which is the part where the ball is being accelerated to some velocity. And so in this case, they tell us that the initial velocity is equal to 0, meaning it starts from rest. So that's our first known. And so then we also know something about the positions. So let's look at that. So we know, for instance, that the position y final is going to be equal to 2.2 meters. And so we see that basically saying, it tells us that Sam lets go of the shot at 2.2 meters. So that's the point where it goes from stage 1 to stage 2. And so then, similarly, we can find y naught, but we're not actually given y naught in the problem directly. What we're given is a distance to where he lets go and a distance over which it is accelerated. The shot is accelerated. So if we look here, we really want this distance. We want the distance from the ground to where the shot starts out. So if we see that is going to amount to 2.2 meters, so the height that it goes to, and we want to subtract off the distance it's accelerated. So this distance here will just be 2.2 minus 0.64. And so that should give us a distance of 1.56 meters. So that's to say the shot starts out 1.56 meters above the ground. So make sure you understand that step of logic because that's going to be important, and we're going to now include that as our initial y above the ground. So we have our velocities and our positions. So one other thing we know is going to be our acceleration. And this is given to us very directly in the problem. They tell us that he accelerates it with a rate of 35 meters per second squared. So here are some quantities that we know. And now if we look at it, one thing we don't know is time, but that is not going to come into play here. And the reason you can see that is thinking, what do we eventually want to solve for? And so the answer to that is a height, so we want a position, and the amount of time this takes really isn't going to affect that, whereas something like the final velocity, for instance, will directly affect the height. And that's just to say, if you think throwing a ball up in the air, the faster you throw it in the air, the higher it's going to reach. So this velocity final is going to be very important to us when we go to our second stage. So we now look, and we actually have quite a few, we have 4 knowns, and we really only have 1 unknown, so it's probably not surprising that if we look at these equations, this third equation, for instance, will allow us to solve directly for our velocity final. So I'll allow you guys to plug in these values and actually do that at home, but you should get an answer that the velocity final should be equal to 6.69 meters per second. So this is the velocity that the ball will leave Sam's hand with. Again, remember this stage is just when he's accelerating it and the ball is in his hand. As soon as it leaves his hand, it has a final velocity of 6.69 meters per second. So this is also going to tie us into our second stage of motion, which is right here, and I'm labeled that B. And that's to say that this final velocity of the first stage of motion is equal to the initial velocity of the second stage. So I'm going to write that down here, and make sure you guys think of that and understand why that is the case. And so the reason is, as soon as he lets go, you go from the first stage to the second stage. So whatever velocity he ends up with at the first stage must be the velocity that the shot starts out with as it goes through its free fall motion. So again, make sure you guys are internalizing this, but this is sort of the connection between stage A and stage B. Okay, so now we can solve for some other things. So our y here, we don't actually know, right? And so we want to decide what y are we looking for. And so in this problem, they tell us we're looking for the height. So we're looking for when the final position is equal to the height. And again, this is unknown, so we still don't know anything more, but this is actually going to be our answer. So if we can solve for y directly, that will also be equal to our height by definition. So what we do know, however, is y naught. And the y naught here is 2.2 meters. And so again, that's just to say it tells us he lets go of the ball 2.2 meters above the ground. So that's our y naught for stage B. And then our acceleration for stage B is going to be equal to minus g. Again, it's in free fall, so by definition, the acceleration of an object in free fall is just gravity, and we've defined up to be 0, so this gravitational vector must be pointing down, which is negative here. So we also now want to look at our v final, right? And so we don't know anything about time, and so the only other quantity we could look at is v final. And so this is going to go back to the very beginning, the intro part of this video, which is to say what is the v final if we're looking at the position when it's at the top of its motion. So if we remember back, what happens if you throw a ball up, or in this case a shot up, is it's going to slow down, slow down, slow down, slow down until it gets to the top, whereby it looks like it sort of pauses for an instant until it starts falling down. So the top of that motion, basically the highest height that it's going to reach, is going to occur when the velocity in the y direction is equal to 0. So make sure that this is a step you guys are internalizing, because this will come up again and again, and it's also very important. It's basically saying that at the point when the velocity reaches 0, we know that must be the turning point when it's just about to fall down and when it's done rising. So that is what we call the top of the motion. So this isn't given directly to us, but it's sort of implicitly given when they ask for the top of the motion. Okay, so now that we have all of these quantities, we can actually directly solve these in the same equation, the same third equation, and we can solve directly for our y. So again, our y here is actually going to be equal to our height, and this is what we're looking for the whole time, and so if we plug in all of these values, we can actually solve directly, and we should get that this reaches a height of 4.49 meters, and again, this is defined above the ground. So I'm going to box this because this is our final answer. So this tells us that once Sam lets go of the shot, it is going to reach a height of 4.49 meters above the ground. Okay, so let's summarize what we've just done. We started by drawing a diagram and pinned down our coordinate system, and we were careful to note that there was 2 stages of motion inherent. Then we looked at the first stage to start, and that was when the ball was still in the person's hand. So we wrote down the knowns, and then we saw right away that we could solve directly for the final velocity of that first stage. We then realized that this became the initial velocity for the second stage of motion, and again we looked at the knowns, and then we remembered that the final velocity here is implicitly defined as 0 for the top of its motion. And then this led us directly to solve for the relevant equation of motion for height, and we took into account the positions where we defined the 0 position to be the ground. All right, I hope you guys learned a little something about free fall motion. So this is something we'll be extending in the future in terms of we'll go to 2 dimensions and then we'll get a little bit more complicated. So if you guys have any feedback about this video or any of these videos, please leave that on the course webpage. And thanks for watching.